Yeah, hi. Welcome to Prop Stat 6. This is the continuation of the previous class. So, previously, um, we discussed about the goals of probability and statistics. So, we discussed all about this part, right? Types of uncertainty, um, then what is a system, what is a model, right? Random variables, how to pick random variables. Um, then we saw the two ways, which is the frequentist and the Bayesian way of, or rather, we just briefly discussed the Bayesian way, and we looked at the frequentist flow on how to decide a random variable and how to quantify uncertainty in this, you can say, in this method. And we briefly looked at, or rather, we looked at the definitions and graphs of the distribution functions, right, which is our PDF, PMF, and CDF. We checked it on this dataset, and that was the end of the first part. Now, in this class, we'll be looking at empirical versus theoretical probability with a case study. So this is the case study. Let's begin with this one. So just to give you an overview, we'll be looking at the case study on, we'll see the practicals, which is the empirical approach. We'll see practically how we'll simulate the real world experience using Python, and then we'll look at theoretical approach as well. And the reason I've already explained previously, right? Why we, or rather, the need of empirical and the need of theoretical. So empirical, this is actually what the reality is. So we need to know what the real world data says, but we need theory in order to predict the future. So, the model theory helps us. How do I put? Yeah, the theory helps us predict the future and future capacity and all of that, all of those things. So, while empirical data gives us the real world what it is right now, and based on that we can we validate with the theory and either plan for the future or try to predict what can happen in the future, etc., etc. So we'll be looking at something called expectation as well within these two approaches, and then we'll be looking at the distributions, which is the model, which is like um, one of the important aspects of the core aspects of modeling in stats, right? A model is essentially set of distributions, plus of course the parameters, plus the data space, all of that, but primarily it's the distribution. So that's the agenda. We'll see. Let's begin with understanding the question. So let me. So the question is: the bag has 3 red balls and 2 blue balls. Let me. Oh, I think I did not. 1 second. Okay, so the question says a bag has 3 red balls and 2 blue balls. Let's draw the bag once just to visualize it. So it has 3 red balls. 1, 2, 3, and 2 blue balls, right? Okay, now actually I could have used this one. No. Yeah, that's fine. I guess that's fine. Anyway, now so we have three reds and three red balls, two blue balls. So what's it saying is you pick a ball, write its color and put it back in the bag. So we are basically picking one from here, I'm checking the color and then I'm putting it back. So if you've gone through the previous classes of combinatorics, etc., we know what this process is, right? It's called replacement, placement or repetition. And this is done 4 times. So the experiment here is picking the ball 4 times. So if all 4 times the red ball was drawn, you win rupees 150. So if these are all reds, we win 150. Otherwise we lose 10 rupees. So the main question is, would engaging in this game result in a profit or loss for us? So the way to again, we will approach this in 2 ways. One is the empirical way and theoretical way. So let's So again, let me just briefly tell the probabilities here. Obviously, this is pretty straightforward. To get a red here now, the probability of getting a red would be how many? 3 out of total 5, right? No matter how many times I try to pick red, it's going to be 3 out of 5 because it's with replacement. The total set of balls are not getting reduced, right? Because every time we pick one and we are putting it back again. So it's always going to be 3 out of 5, P of R, and P of B is always going to be 2 out of 5 as long as replacement exists. So with that in mind, let's try to simulate this using Python. So let me install numpy. This is again standard procedures, just to be clear. Install, just to be sure, pandas matplotlib dot pyplot C1. We'll also be using something called SciPy when we'll be handling binomial distribution and Bernoulli distribution. We can actually do this directly in Python itself. Also calculating expectations as well. So we'll see. Mostly everything will be satisfied, other than I think SciPy is kind of new. So we'll see. Import numpy as np, import pandas as pd, matplotlib.pyplot SPLT import P1 SSNS import SciPy dot. We'll be using the stats submodule as let's say SC. SC. Let's do SCI. That's good enough. Anyway, now we have the imports now. So just to remind you, we are doing the empirical approach. So okay, so just to give you some background of a coin toss. So there was a scientist who actually performed 10,000 coin tosses just to verify whether, just to observe how many heads and how many tails in general. So if the sample size is small, you generally will not have correct, you will not get the correct true probabilities. So in order to get true probabilities, you have to take large sample sizes. So for example, if you are trying to pick a ball, let's try to simulate that. How do we do this? We can first of all see, we want 4, right? What is the question? We are picking a ball and putting it, checking the color and putting it back, and this is done 4 times. So out of these 5 balls, I want to pick 4 times. So the way we will do it is, we will first of all, and this is randomly being chosen, right? It's not like we know it. So we can use a randomizer here using np.random dot okay, coming to random, I think we also need math. What math? Okay, so we'll use the np.random.choose, and we want to choose between, okay, let's look at the is it choice? Yeah, it is choice. Okay. So if you see the signature and the parameters, it's a 1D array. So the first parameter, it's accepting a 1D array. A random sample is generated from its element. So from what elements we need the random samples? We want the random samples from 3 reds and 2 blues. So we'll just create reds this way. 3 reds and 2 blues. Okay, these are our samples. And the second parameter is size. Intertuple optional output shape. So what output we want? We want what is happening? What output we want? We want we want 4 out of these 5 options, right? Every time we in every trial we want 4 options. So size will be 4. I think that is sufficient. Now if I run this, you will see I got in this experiment I got 1 red one blue and another red. So I got 2 reds and 2 blues. If I run it again, now you'll see I got blue, red and blue. If I run it again, you'll see I got blue, red and red. I got 3 reds. Let's see if I'll get 4. Oh, I got all 4 reds. Right, so this is how we'll be playing this. And since once is not sufficient to capture the to actually rather how do I put it? Yeah, so to get the true probabilities, we'll simulate it multiple times to see what is the actual probability of getting 4 reds or 3 reds or 2 reds or 1 red or no reds at all, right? We might not get reds at all in these when we pick 4 of them. So yeah, let's do this 10,000 times. So what I will do is, for trial in range 10,000, I will first I will store this choice, or rather I'll freeze the selections made. Selection in a variable, and then what I will do, rather what we can do is, yeah, so we want to know how many reds we got, right? So if we see here, the way we can store the number of reds, we can do something like, if I want to know the number of reds, what I'll do is I'll store reds equal to, we'll see how many reds we got. We got 3 reds, right? So how do we capture this? We'll do something like reds, we'll use a mask, boolean mask, reds equal to, I want all the r's. Let's see, I got all my r's, and all I will do is take the length of it. I got 3 r's, right? Let's call this also reds. Now let's call it length. And now what we can do is we will store this. Actually, 1 second. So the objective we are trying to achieve is, we are trying to see how many times 4 reds came, 3 reds came, 2 reds came, 1 red came, and 0 times red appeared when we performed this experiment 10,000 times. So in each trial, how many times red appeared? So I can capture the reds. Yeah, that's correct. So I'll just store it in a list. Red count, rather red list equal to. Now I'll just append this value, and if we see the red list, we have a long list of threes and twos and threes and twos. So 3 means 3 times we got red, 2 times we got red, 0 times we got red, 4 times we got red. Now all we have to do is check value counts. Okay, we cannot do value counts on a list if I'm not wrong. So we'll do np dot series. I'll convert this into a series, and then I'll do value counts. Now if you see value counts, module numpy has no attribute series. Oh, sorry, pandas. Okay, there it is. We will also sort it by index. So if you see, we got 0 times red around 251, or rather, sorry, we got 0 reds 251 times. We got 1 red 1572 times. We got like 2 reds 3000, 3 reds around 4, another 3400 times, and 4 reds we got 1301 times. That is total 10,000. These are 10,000 trials. So now what we can do is we will do a normalize just to see the percentages. So there is a keyword called normalize, which will give us the percentage. So see here, 2% of the times we got 0 reds. Around 15% of the times we got 1 red, right? 34% of the times 2, another 34% of the times 3, and another 13% of the times we got 4 reds. So now what do we do with this data? So let's calculate the mean of this one. Let's calculate like what is the average number of times we are getting red from these proportions. So all we have to do is np dot mean, and if we pass in the red list, we are getting 2.4. So around so we'll get around 2.4 times reds every time on average when we perform the experiment. This is like the you can say this is the expected number of reds we will get when we try to pick when we try to pick 4 times, we will get an average of 2.4 reds. Now why is this 2.4 reds important? Because if we have to model the random variable here, what is the way to win this game? The way to win this game is to get 4 reds, right? So that is the so that is the reason why we are looking at this expected value. So the expected number of reds is 2.4 in this case. Just because you got the average as 2.4, it does not mean that these are your winning chances or something like that. It's just a way to understand whether to play this game or not, or rather you're just trying to take an informed decision. Because if let's say you got less than 2 or maybe less than 1 or something like that, this game is you can immediately ditch this game, because your chances of winning could be very low, right? This is uh, yeah, it's just a way to make decisions, take calculated risks. So this expected value is actually a weighted mean. In this case, mean and weighted mean will be the same. If we take the weighted mean of this, we can use np dot average. Yeah, so the average takes arguments. It takes the list value. So we can do something like count is dot. So the count is the weights. No. The count is the index, and the weights are. Let's do one thing. Let's call this x, and can do count equal to x dot index and x dot values. So this will be count comma the other argument, if I'm not wrong. Yeah, it is weights. Weights equal to weights. So let's see the invalid syntax. Maybe you meant equal to. Okay. So you see here, mean and weighted mean both are 2.4. Now why is that the case? Because we are actually working on the real frequencies here. So you see, these are the weights. The count here are the weights, and 0, 1, 2, 3, 4 are the values. If you see GPA and all, GPA is randomly assigned. So, I mean, not randomly, but it does not reflect the count of the subjects or anything like that, right? So, if you have a GPA, let's say, you'll have grade and you'll have marks. So, suppose you have you got 30 marks, you got 70 marks, you got 80 marks. So, this maybe this subject, let's say it's physics, chemistry and maths, right? Let's say physics has a grade of you got a 4 out of 5, and chemistry you got a okay, I guess let's say 2 out of 5, and you got a 3 out of 5, and you got a 4 out of 5 here. So this 2 does not reflect the frequency. It's just an arbitrary value that we have assigned. However, here the count actually represents the frequency. So we have 0 to 51 times. So that's like the correct frequency of things. So which is why in this particular case, the mean and weighted mean, you will have the same value. So that's the thing. So this this weighted mean is called expected value, and this is what we use to make decisions. So we checked why mean and weighted mean in this case are the same. So let's try to get the formula of expected value. So right now we are trying to calculate the empirical expected value of a random variable. So expected value is nothing but the weighted average values of the random variable uh, um, when the probabilities are uh, given the probabilities. So probabilities of those values, which is just the weights, it's times the probabilities of the value. So let's say if we take this example, this thing here, let me just take this down. So I have 0 to 51 times, we have 1 1572 times, we have 2 3 4 0 4 times, we have 3 3472 times, and we have 4 1301 times. So if we try to so what is mean? Basically sum of terms by number of terms, right? So basically what did we, the way that got computed was so 0 251 times. So what is it? So like 0 plus 0 plus 0 plus 0, this is basically going to be 0 anyway, 251 times. Then we have ones, like you have 1 plus 1 plus 1 plus 1, so on. This count is like 1572 times. So basically what is that? 251 times 0 is 0, plus 1572 times 1, right? 1572, that will be 1572. And then same with the 2's. So 2 plus 2 plus 2 plus 2, that came 3404 times, right? So all we have to do is 2 times 3404. Same with 4's. All we have to do is 4 threes. So 3 times 3472 plus 4 times 1301. It is 1301, right? Yeah, it is 1301. Divided by number of terms is what? 10,000. Right? These are all the terms. Now if you look at the structure here, so this is again we are trying to compress this equation, and rather we are trying to find a pattern from this from this setup right here, and we are trying to find a small elegant pattern which we can use. So this can be rewritten as 0 times 251 plus 1 times 1572 plus 2. So we can rewrite this as this way, right? Because this is basically we just took a common denominator and then we are adding everything. So I can do something like plus 3 times 3472 by 10k plus 4 times 1301 by 10k. So what is this? This is basically these are our probabilities, right? What is the probability formula, which is possible outcomes by total number of outcomes. So if you see here, 251 by 10k is nothing but 0.0251, the normalized version. Same with 1572 by 10k is 0.1572, same with the other value. So these can be rewritten as 0 times p of 0 this can be rewritten as 0 times P of 0 plus 1 times, 1 times P of 1 plus 2 times P of 2 plus 3 times P of 3 plus 4 times P of 4. That is basically how we can decompose this, right? So this can now be, we can just use the summation symbol sigma, because that's basically the addition, right? So that is where we can say E of x random variable, the random variable x is nothing but summation of, so we'll say I equal to 0 to n xi, which is our random variable, times the probability of x equal to xi. That is how we can say derive the formula. So if from this we can say the definition is basically the random variable times the probability. So it's the weighted average of the random variable times the probability of the random variable. So that's basically what expected value is. I hope that was clear. I don't think there is anything else that I have to say. Yeah, I think that's it. So where is this expected value used? Again, this is the value that people check to make decisions. So this is used in many places. So you can use it in basically all many tech companies, it seems, use this in A/B testing, right? So the heart of the, or rather the situation can be something like, if you have let's say I have a button color here, so there is some teal color here, right? So if you see here, now this button color, my conversion rate, or okay, let me not use this one. In fact, let me just say there is Amazon website, and there is a buy now button. They have an orange color, right? So let's say that is giving them some amount of conversion rate, like let's say maybe 3% or 4%, whatever. Like, I'm not giving exact values. It's just an example. Now, if I change that button color from, say, from yellow to, say, blue or green or something, now the conversion rate increased by maybe, let's say, from 3% to 3.5% or something like that. So what is the expected revenue that is generated by changing this color? So something like that. So A/B testing, similar thing can be used in recommendation engines as well. So you can ask something like, if I suggest movie X versus movie Y, which one is going to give me greater revenue? What is the expected revenue when I suggest movie X instead of movie Y? Or even same for fraud detection. Anything where you have to make comparisons and ask a question, is this going to reduce the fraud or increase the fraud? Is this decision going to make me more money or make me less money? So something like that. in all these scenarios we can use the expected value. um, um, so let's take an example. Let's say there is a small e-commerce company wanted to implement a save for later feature. So there is a, let's say, save for later button. There is a save for later button and like a on every product or something like that. Let's just say there is one, right? So should we build this feature or not? Now, in every tech company, obviously, when you want to implement a feature, first of all, you will obviously there'll be the dev cost, right? The developer cost will be there, then the designer cost will be there, and then the QA cost will also be there because they have to test the feature. So let's say the dev cost for this save for later is, I'm just taking random numbers. Let's say this costs around 3,000. The designers cost around maybe 2,000, and the QA costs around 1,000. Just some random numbers. So 3 to so around 6K, right? So this feature costs around 6K. Now the let's look at our so this is the cost of the development. Now let's check the metrics of this company. So they say this company has users around 500K, right? Maybe let's take 50K, 500. I don't want to make the numbers big anyway. So they have around 50K users, and their order value is around let's say around 20K order value, right? And what else? Conversion rate. Let's check conversion rate. Conversion rate, they have about 3%. Currently, this is the current state. Without save for later feature, right? So this is without save for later. Now, after implement, so generally, the way product managers suggest features is largely dependent on the prior knowledge and of course some intuition as well, because new features, otherwise if that is not present anywhere, they will have to make some sort of informed decisions based on A/B testing and all that stuff, based on intuition, based on A/B testing, based on competitor data, based on a lot of other subjective and objective things. So upon all this user research, what they have concluded is they have come up with 4 scenarios. Let's call it S1. Scenario 1, which is there are some standard names called like a strong success. Then S2 will be medium success. S3 will be weak success. I mean, it's not just these 4. We are just taking these 4 scenarios right now. These are not the only names. And then S4 let's consider it as a failure. So in S1, what we are saying is strong success. In this case, the conversion rate increased. So we are assuming the numbers. Based on the research, we are saying the conversion rate can increase by 0.6%, right? In scenario 2, the conversion rate increased by 0.3%, scenario 3 by 0.1%, and scenario 4 failure, it went negative, so negative 0.1%. So based on this, we can actually extrapolate, or rather we can actually calculate the rather the revenue as well. Okay, it's the revenue we have to calculate. So what is their current revenue? Current revenue is so 3% of 50k is what? So 3 by 100 into 50, that would be 3 by 2, 1.5. So 1.5 times 20,000. So their current revenue is around 30k, right? So what I did, 3% of conversion rate out of their 50k users. So 3% of their 50k users are paying 20k every year, let's just say. So their annual revenue is 30k. These are hypothetical numbers. E-commerce sites will get way more, but let's just say it's in its early stages. So so now we can calculate the revenue based on this one. So 0.6% increase, so this will be 3.6%. I don't want to do these calculations now. This lecture will go too long. Let me just give you an overview. Let's take some random numbers here so that it's easier for me to calculate. So here they gave a probability of 25% probability of a strong success. Here they gave, let's say, 30% of medium success and around 40% of weak success and around, let's say, around 30% of failure, right? Now we are trying to, what are we trying to do? We are trying to calculate the expected value, right? The expected value, as we saw, is just the sum of rather it's the weighted average of the values, the revenues in this case, times the probabilities, right? So let's say this came around let's say 36k. That the next one came around let's say 33k, another 32k, and then the third one went below 31k, and the one went below to 29k, right? Times the probability. So 36 times 0.25 plus 33 times 0.3 plus 31 times 0.4 plus 29 times the failure is also 0.3, right? Now when I sum all this, I will get a value. Let me just sum this. Is there a way to? No, I don't think it will calculate. So let me say 36 times 0.25 plus 33 times 0.3 plus 31 times 0.4 plus 29 times 0.3. So that will give us around 40. So this is giving us okay. Okay, so the expected value is, or our expected revenue is 40K from this. Yeah, now we can calculate the expected profit. Profit is basically we just have to subtract from the capital expense of making this feature from our revenue, right? So 40K minus minus what is our building cost? 6K. 6K. So the expected profit is around 34K, right? Clearly this is a good investment. So we can calculate the ROI. So return on investment is calculated based on expected profit by cost of feature times 100. So in this case expected profit is 34K by cost of feature is 6K times 100. This is 2 3 let me just 34 by 6 times 100. So it's a massive 567% return, right? Our ROI is 567%, which is pretty great. So clearly the decision should be we'll build the feature, right? So this is like a rough way, how is like just an overview of how expected value is used to make much more informed decisions. So that is so that's about the empirical approach. Now let's go to the theoretical approach. So let me just connect this, it got disconnected. So the question, once again, if we look at the question is asking, this is done 4 times in total. If all 4 times the red balls were drawn, you win 150. So if all 4 times the red balls are drawn, then we get 150, and otherwise we lose 10 rupees, right? So would engaging in this game result in profit or loss? Let me just run all these once again. So we'll solve this by answering some questions, simple questions, and then we'll progressively go on to derive the formula and then calculate the expected value. Actually, yeah, we can derive the formula, but that's actually binomial distribution formula. But anyway, we'll see the expected value and then compare the empirical results with the theoretical results. So the first question is probability of one red ball in one draw. So if I have to put it, So it's saying probability of one red ball in one pick. We can also rephrase it as what is the probability of getting one red ball in one single draw. So this is pretty standard, right? We have, if we look at the if we look at our the bucket, which is the balls. Let me just copy this. Let me name this as strange. 1 second. Okay. Theoretical approach, and this is our bucket. Okay, so three reds and two blues, right? So the question is pretty straightforward. If we pick a ball at random, what is the probability of that ball that we picked being a red ball? So pretty straightforward. P of R will be, we have 3 reds out of total 5. 3 out of 5. The next question is probability of let me just put in different one. So what is the probability of getting one blue ball in one pick? Again, P of again very straightforward. P of B will be, how many we have? 2 blue balls out of 5. Right? Then now they are asking what is the probability of getting 2 red balls in 2 picks. So we are drawing the ball 2 times. What is the probability of getting 2 red balls? So this whole thing, you see, this is a replacement question, right? You pick a ball, write its color, put it back in the bag. So this is with replacement. So the probabilities will remain the same in every draw. So in this case, they are asking probability of 2 red balls in 2 picks. So first time, first pick, what is the red ball probability? 3 out of 5. Second pick, let me put it here. Second pick as well. The probability will remain the same because I put the ball again. So I still have 3 red balls. So again in the second pick, I'll have 3 red balls. So the question is probability of getting 2 red balls in 2 picks. So the experiment here is 2 picks. So in a single trial, we are performing 2 pick. We are drawing it twice. So there is a joint probability. So joint probability, we know the formula, right? Joint prob, which is P of A intersection B. So these 2 events, event A and event B, happening together, which will be nothing but P of A into P of B. This is P of A into P of B because when we are replacing the ball, the event automatically becomes independent. So the next time you pick a ball, it is not being affected, or it will not affect any other event, right? Because it is simply we are picking the ball, we are putting it again, so the state is back to the norm. It's so it's like a fresh event. Every event is every time you you pick, it's a fresh event. So that is why. So the probability of two reds here will be 3 by 5 times 3 by 5. That will be the probability of two reds. Now if we look at the next question. Excuse me. So what is the probability of one red ball in first pick and one blue ball in the second pick? Again, pretty much the same question, but instead of two reds, here we have now one red and one blue. So P of red and blue. So probability of red is nothing but 3 out of 5 times probability of blue is 2 out of 5. Again, the same concept. In this experiment, these we are picking twice. So both the picks are happening in the same experiment, in the same trial, in this experiment and in the same trial as well. So no, in the same experiment, and we are doing one trial. This is one trial, and both the events must happen together. So it can happen. I mean, it does not matter if they are simultaneous or one after the other. They should just happen together. And since we are replacing the balls, both are independent events, because picking one ball does not. So me picking a red ball does not affect the probability of picking a blue ball here. So that is why it's going to be 3 over 5 and times 2 over 5. Now the next one. What is the probability of one blue ball in first pick and one red ball in second? I think we already did that. No, okay. It's the reverse. It is the same. It's going to be the same. It's going to be 2 by 5 times 3 by 5. Now let's look at the next one. So this, what it's saying is, what is the probability of getting red, and blue when we pick the ball 4 times. So in this, the experiment is 4 ball. We draw the balls 4 times. We draw each ball 4 times, and they are asking what is the probability of getting in this sequence: red, and blue. It's still the same. The concept is the same. It's the joint probability, and we'll just have to compute individual probabilities for each of these. And since it's replacement, it's going to be exactly the same. Each probability of drawing each red ball is going to be still 3 over 5 for all 3, and probability of blue will also be 2 out of 5, and this will be the total probability, and it will be the same for all these 2 as well. The result will, you just have to, for blue will be 2 over 5, and rest of them 3 by 5, 3 by 5, 3 by 5, and here it's all blue, so all of them 2 by 5 times 4, right? Sorry, 2 by 5 over 4. 2 by 5 power 4. I think that is over 4. No, I think it's power 4, not over 4. So that's just how we do that. Now let's come to the main question, which is, what is the probability of obtaining one red ball out of 4 balls drawn? So this is this scenario. Somewhat similar scenario, but somewhat similar here, although it's blue. But what this question is asking is, when we draw the ball 4 times, so first ball can be a blue, second ball can be blue, third ball can be blue, fourth ball can also be blue, right? If we try again, rather, if we stick to the question, probability of obtaining 1 red ball out of 4 balls drawn. So let's say I got the last one as red. I can also get this way. So I can get blue, blue, red and blue. I can also get blue, red, blue, blue, and I can also get red, blue, blue and blue. These are the 4 ways, or rather 4 arrangements that will give us 1 red when we draw the ball 4 times, right? So what is this basically? This is nothing but 4c1, right? 4 factorial times 1 factorial, 4 minus 1, 3 factorial. It is nothing but 4 into 3 factorial by 3 factorial, which is 4 times. So you have 4 times. Now the question is, what is the probability of obtaining 1 red ball out of 4 balls drawn? So now we have to compute the probability for each of these scenarios. So let's call them case 1, case 2, case 3, case 4. So in case 1, we will have, what is it, blue balls, probability of blue is 2 by 5 times 2 by 5 times 2 by 5 times 3 by 5, right? Which is nothing but 2 by 5 whole cubed times 3 by 5 power 1. If we look at case 2, the probabilities now will remain the same, because in each of these cases you will have 3 blue balls and only 1 red ball, right? So this probability will remain the same, but if we compute just one more, just for example's sake, so you'll have 2 by 5 blue ball, red ball and blue ball. Once again, same probability, you'll have 2 by 5 whole cube over 3 by 5 power 1. So like this you will get ditto for C3, for case 3 and case 4 as well. So we can write this as 4 times 4 into 2 by 5 cubed times 3 by 5 power 1. So why did we, now we understood why we are multiplying, right? Because it's joint probability, we are since all of them have to happen within the same event, we use the AND condition here. But if you see this is the question is asking probability of obtaining 1 red ball out of 4 balls. So the experiment itself, so what is the experiment here? The experiment is draw 4 balls, right? So what will the sample space look like? The formula for sample space is outcomes power number of trials, right? So what are the outcomes? So the drawing a ball. So if I suppose I for a draw random ball, what are the outcomes I can have within these? I have 3 reds and 2 blues, right? So what are the possible outcomes I can have? I can either have a red ball or a blue ball, right? So my sample space is 2. So if I say 2 power, number of trials here is how many? We are performing 4 in 4 trials we will get these we will get 1 red. So this is a let's see. Excuse me. So power 4, that is what? 2 into 2 into 2 into 2, which is 16. So this will have 16 outcomes, and the 16 outcomes can look like what? So since their experiment itself is 4 balls, so the each outcome will look like something like red, 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 or red, 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 blue, red, red, blue, red, so on, so on, so on, 16 of them, right? 0, 1, 2, so on, 16 of them, 15, 16. So you'll have 16 outcomes like this, and out of these 16 outcomes, you will have an event, and this is our event. The event they are asking is what is the probability of getting 1 red ball out of 4 balls drawn. So these are 4 balls drawn. Out of these, the event where 1 red ball can occur is basically blue, 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 red, blue, blue, red, blue, blue, red, blue, blue, and red, blue, blue, blue. Right? These are the 4 outcomes where you will get 1 red, which is why you have to add all these here, because if suppose when we perform the experiment, when we get the first outcome, let's say I got this, automatically these cannot be considered, right? Because these are each event here is mutually exclusive. So if this happens, then this cannot happen. It's just like heads and tails. If I get heads, then automatically I'm not getting tails. So if I get blue, 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 and red when I perform the experiment, automatically that means I'm not getting blue, blue, red, blue. I'm not getting blue, red, blue, blue, and I'm also not getting red, blue, blue, and blue. So since each of these are mutually exclusive, these are OR conditions. So I can have case 1 or case 2 or case 3 or case 4, which is why I will have to multiply by 4 to this particular event, and that is how I will get my probability. So this is basically my probability for this question. Probability of obtaining 1 red ball out of 4 balls drawn. Now let's look at the second one, which is what is the probability of getting 2 red balls out of 4 balls drawn. Now they are asking 2 red balls. So if we look at the combinations, that will increase to 4C2, right? What is 4C2? 4 factorial 2 factorial, 4 minus 2, 2 factorial, so that is 4 into 3 into 2 factorial. So this 2 and 2 will cancel, and 2 is 4, that is 3 into 2, 6. Oh, 3 into 2, 6. So we will have 6 outcomes where 2 red balls out of 4 balls that are drawn. So we'll get 2 red balls out of 4 balls drawn in 6 total outcomes. So the total outcomes can be something like so it can be blue, blue, red, red. We can have blue, red, red, blue. Okay, this is going to be tricky. Wait, blue, red, red, blue, blue. Then I can have blue, red, blue, red, right? I can have red, blue, red, blue. I can have red, blue, blue, red. So I have 1, 2, 3, 4, 5, 6. So those are 6 outcomes. And obviously the procedure remains the same. We will calculate the probability of blue is 2 out of 5 times 2 out of 5 times 3 out of 5 times 3 out of 5 is nothing but 2 by 5 whole square times 3 by 5 squared. This is for case 1. The probability value will remain the same for all 6. And since each of them, these are all mutually exclusive, each event, you will have 6 times, each of them is an OR condition, so we'll multiply by 6 into each of these probability of a single trial for 4 balls drawn, which will be nothing but 2 over 5 square times 3 over 5 squared. So this is the probability for this question. What is the probability of getting 2 red balls out of the 4 balls drawn? Right, I hope that was clear. I think that is it. Then now if we want to derive the formula, okay, so the question, if we now getting back to our original question, these are all dummy questions right now. We just this is just for understanding the main question, which is the probability of winning is if we draw all the 4 balls as red, right? So we can use the same method, the way we calculated probability just now, for single red, for 2 reds, then we'll calculate 3 reds and 4 reds as well. We will, and once we do that, we will get the winning probability. But now calculating for 4 reds is basically 4C4, right, in this case. And obviously the calculation will become tedious. So from this, what we can see a pattern here, right? So we have, this is nothing but 4C2 for 2 reds, where we are performing 4 trials, right? 4 trials, and we are looking for 2 reds, and this is probability of P of what? This is P of blue times this is what? P of red. Power, we'll see the power, but as you can see here, we can we are able to see a pattern there. Again, this is what? 4C1, This is probability of blue, and this is probability of red, right? So if we want to compute the probability for where there are no reds, which is p of x equal to 0, up to p of x equal to 1, where 1 red comes, 2 red comes, 3 red comes, and 4 red, all 4 draws are reds. If we want to compute that, the probabilities for all of them, then we can use the formula which is number of trails. So number of trails here is 4, and the random variable is the number of red balls drawn, right? So we can do something like p of x equal to 0 can be something like 4c0 times probability of red. So p of r in this case, power number of reds are what? 0, power 0 times p of blue will be automatically what? If reds are 0, that means p of number of blues will be 4, right? If there are no reds in the 4 draws, that means all 4 are blue. So from this, what we can do is we can actually say something like p of x equal to k, where k is the number of reds. Let's suppose you can say 4ck into if we take p as the probability of reds, which is nothing but p power k times what is the, so if we say the success is probability of reds, then the failure is automatically 1 minus probability of reds, right? Which will be nothing but 1 minus p power, if I have used k here, then the remaining will be what? 4 minus k. In this case, which is nothing but n minus k, right? Because I already used k. If red occurred for 4 times, or if red occurred k times, then the probability of everything else, then all others occurred n minus k times, right? So that's why we have n minus k here. And in this case, there are only two outcomes, right? You can either have red or you can have blue. There are no other scenarios. So from this, we can actually compute p of x equal to 0, p of x equal to 1, p of x equal to 2, p of x equal to 3, and p of x equal to 4. So we plug in to each one of them. I don't know if we should do that. This looks tedious, but anyway, we'll see. Which is nothing but 4c0 times p power, in this case p is number of reds, which is the probability of reds is what? 3 out of 5, right? Power 0 times 1 minus 3 by 5 power 4 minus 0. Oh god. I just want to simplify this. I don't want to calculate all this. So it will be the same, right? For, let's say, for 2, it will be 4c2 3 by 5 square 1 minus 3 by 5 power 4 minus 2, because k here is 2. Same with 4c4, 3 by 5 power 4, 1 minus 3 by 5 power 4 minus 4 is 0. So anything power 0 is 1, and this we can calculate. So I will make my life simpler slightly. I don't want to waste too much time in calculation. So you know what? We'll just do it in Python. Yeah, we'll do it in Python. I think that is the best way. Yeah. Let's do it in Python. So this will be, so for combinations we can use math.com. Let's see, n and k, n binomial coefficient, and ck, right? So for we are doing for p of x equal to 0. So we do for n and k. Let's see, what does it give? So 4c0 is 1. How come 4 factorial by? Ah, yeah, okay, 4 by 0, fine. It is 1 times 3 by 5 power 0 is nothing but this is also anything power 0 is also going to be the same, but 1 power 0 times 1 minus 3 by 5 power 4 minus 0, it's going to be 4, 4 anyway. So we'll use the same for all of them. So let's see what this will give. This gives 0.025. Now for 4c1, 3 by 5 power 1 minus 3 by 5, 4 minus 1. Here it's 4 minus 0. This is 4 minus 1. Minus 0.9. Hold on 1 second, something is wrong. 4c1, 3.5. No, maybe that is correct. Okay, wait. This is 2, 4c2, 3 by 5 squared, and 1 minus 4 minus 2. Okay, 4c3 power 3 minus 2.97 and 4c4 3 by 5 power 4 minus 4 minus 3.99 minus 3.9. Okay, I think this is the problem. It should be in parenthesis. So then, okay, see, that is the issue, I think. Yeah. So these are our theoretical values. Now if we compare them with what we got here, so you see here 0.02, pretty close. Let me get these values here again so that we can just compare directly. So you see here, the first one is close to 0.023 and this one is 56. So the theoretical is 256 and our experimental came to 238. Theoretical is for P1 is 1536, 1545, pretty close. For x equal to 2 is 3456, 3461, again very close. 3455, 3448 and 1296, 1308. So you are seeing the difference because our sample size is just 10,000. So as we increase the number of trials, not sample size, I'm sorry, it's the number of trials. So we only did 10,000 iterations, right? So if we perform more, our empirical will start converging with the theoretical values. So that is how. So that's basically the empirical and theoretical approaches. How we can compare them and see how well our model fits the reality. So we derived the formula. Now we'll look at the expectation value. Did we calculate expectation before? I don't think so. So again, I think we did the expectation, right? If PD, where is expectation? I'm pretty sure we did expectation. Weighted averages. Did we not do weighted average? Wait, I think somewhere here we did. Expected value. Yeah, there is our expected formula. We have okay. Did we not calculate the expected value? I think I forgot to calculate the expected value. 1 second. P0, P1. Okay, so let's calculate the expected value. So here we have the probabilities. So the weights, let me just put them in variables. P0, it's going to be P0, P1, then P2, then P3, P4, and all we have to do now is we know the expected values, right? So the weights times their probabilities, which is P0, sum of the weights, weighted averages times the probability. So 1 into P1 plus 2 into P2 plus 3 into P3 plus 4 into P4 over, what is it? No, not over. That's it. So our expected value is 2.4 in this case. Now, how do we? This is you can say this is our empirical and theoretical as well. I mean, if I just substitute okay, this is our theoretical expected value. If I want to take the empirical expected value, then I just have to multiply this with these values. That will give us somewhere pretty close to this value, this number only. So I can say something like, let's see. I'll do something like reset index now for I in range rather for I in df dot in index list, what I will do is this is going to be empirical expected value. So EE empirical expected value plus equals the index, which is I, times TF proportion let's check EX. You see here we got somewhere pretty close. Empirical expected values as well, 2.4043. Our theoretical expected value is it's called this TE. Theoretical expected is 2.4. Pretty close. So that's how we calculate expected. Now there's one more way we can calculate expected value. We'll look at that. I guess we'll look at that. We'll see that in binomial distribution. So the question basically is asking, would engaging in this game result in profit or loss, right? Right. So how do we calculate this? So we'll look at this from the monetary perspective. So what is the win scenario? So the win scenario is I'll win if 4 reds, and my win scenario is 150. My win amount is 150 rupees. I lose if not above, right? So if it is not 150, I will, and if not 4 reds, I will lose 10 rupees. Which means we can say I will take a new random variable called y, new RV called y, and I will say the outcomes of this random variable are either 150 or minus 10. Now what I'll do, I'll calculate the probability of getting 150. So P of 150 is nothing but, so if you see P of 150 is nothing but is the same as P of okay, y equal to 150 is nothing but P of x equal to 4, right? So if I get all 4 reds, that is same as me winning 150 rupees. And the P of y equal to minus 10 or me losing the game is nothing but 1 minus P of x equal to 4, right? So anything other than 4 reds is when I will lose the match, right? So that's the name of the game here. So if all 4 times the red balls was drawn, you win 150, otherwise you lose. So we just have to calculate this and get the expected value from these probabilities. So what is P of x equal to 4? We already know x equal to 4 here, which is nothing but P4. Let's take the same P4 and so win is P4, lose is 1 minus P4, right? So my probability of winning is 0.129, probability of losing is 0.8704. Now if we calculate the expected value from this, how do we calculate the expected value? Obviously the weights times the probabilities, right? So expected value is nothing but what are my weights here. In this case we are using the money as the weights, right? So if I take the money as the weight, so 150 times what is the probability of winning, which is my P4. What are we doing? Weighted average times the probabilities, summation. So I will add this with the losing weight times the losing probability. If we look at the expected value, it's saying plus 10.735. So what this rupees, by the way, this is rupees. This is the currency. This is the amount we will win on average. So what expected value tells us is the average winning amount in this case. So this is the average amount we will win per game. So what does that mean? It does not mean every time we play we will win. Obviously no, because the if suppose we are playing we will win on an average 10.73, which is approx 11 rupees in every game, provided we play lots of games. So in the long run, on average, we will make 10.7 or 11 rupees per game. So what it means is, if I play the first game, I will lose. I lose. Then I play second game, I still lose. which is minus 10, minus 10. I still lose minus 10. Game 4 also minus 10. Oops. So on. But like say in game 9 I won and I made plus 150. So this one game will cover lots of my losses. So that is how on average I will overall win this, or rather it is overall profitable to play this game, if provided we play this for a long period of time. So that's how the calculation happens. This is the average. So this 11 rupees is the average win amount per game. I hope that was clear. So the conclusion is we should play the game. Should I? So the question was was asking, would engaging in this game result in profit or loss? The answer is yes. Engaging in this game would result in a average profit of 11 rupees per game. So that is the thing. Now let's get into the next topic, which is binomial distribution. So binomial distribution, we derived the formula here. What the definition of binomial distribution is nothing but it is the discrete probability distribution where discrete probability distribution of the number of successes in n independent trials. Discrete probability distribution of number of successes in n independent trials. Obviously discrete probability distribution means these are countable values, and number of successes meaning those countable number of successes in n independent trials. We already saw it in the previous question. Number of trials are 4. They are fixed and they are independent because it's with replacement, right? In this question, the question itself is with replacement. You put it back in the bag. So they are independent trials and they are fixed because we are only doing 4 number of trials every time. And yeah, that is basically it. And one of the things is the outcomes of a binomial distribution can either be a success or a failure. You can either have a win or loss, success or failure. It's a binary outcome. And we already saw the formula because we already derived it here, right? Somewhere here. This is the formula for binomial distribution. This is basically used to get your PMF value. So what is PMF? Just to refresh, the probability mass function. It is what is the probability that I can get exactly a particular value, right, for a discrete random variable. So let's see. um, we can just plot the graph once just to visualize it. Where are the red balls? So we can take this red list and we can use SNS dot bar plot. I don't think so. What is red list again? Is it just list? Yeah, I think it should show to. Do we have SNS? We do have SNS. Cborn, I have math, scipy.stats. Okay. I guess there are too many of them. Oh, okay. Okay. So we should not do it on the red list because there are 10,000 of them. It's trying to plot 10,000 bars at once. So what we'll do is we'll do it on the probabilities. We'll go with this one. There it is. So if you see here, these are our PMF values. So if you see here, each bar represents the probability of a particular random variable, particular value of a random variable. You see here, this one is close to 3.5. This one is close to 1.6 ish. What else? Yeah, basically these are the PMF values for particular discrete random variables. I don't think there is anything else that I can say about this for now. At least I'm not. I don't think there is anything else. So what we can do is. So these are we already calculated PMF values in theoretical and empirical approaches, right? So these are the PMF values, the probabilities. We used this. This is the formula to use to calculate PMF of a particular value of random variable. Now what we will do, but see, calculating this is kind of tedious, right? Like manual calculation. So there is the other way we did was using Python, but still we had to write the equation manually. This way, math.com times 3/5 power 2. This is also pretty tedious. So what? There is a ready-made way of, there is a library called scipy that allows us to calculate PMF directly using a method, using a function, using a method. So we have scipy. So from scipy, or rather, from scipy dot stats import binom. So we use binom binom dot pmf. So if you look at the signature, it takes k, it takes args. So probability mass function at k of the given random variable. Actually, this takes three values, which is k, p, and n. So we have to pass three values. Although this is showing arg1 and arg2, so we pass n equal to 4. P is probability of getting red, right? So in this case 3 out of 5, and k is nothing but our the random variable. So let's say at 0. So you see here 0.0255. Let's see p0. What is our p0? 0.0256. Close, pretty close, right? And we can do the same for k is 1, k is 2, k is 3, and k is 4. So let's compare k is 4. We have 0.1296. What is k4 here? 1296, right? Same. And if you look at 3, it's 0.3456. 3 is 0.34559, pretty same. 0.59, if we round it off, it is 56. So that is how we can directly compute the PMF values without doing manual tedious calculations. Now let's look at the expectation. So how do we calculate expectation? The same way, we can use these PMF values times the weight, and we can sum all of them. That is one way, but obviously there is a direct method. We'll use binom dot expect. So this is used to calculate the expected value directly. So the arguments that we have to pass are so expected value, obviously we have to pass the random variable. In this case it will be 4. So k will be 4. Although this is giving weird arguments here. So obviously we have to pass n and k. We'll pass those two. I am not sure why this method signature is so weird. I think it goes into the args section. So we have to pass n equal to 4 and k. Okay, not n. So you have to pass. I think we have to pass n, not k, or maybe k. Wait. So p equal to 3 over 5. We have to pass the probability, obviously. And is it k? Got an unexpected keyword argument. Is it n then? Discrete.expect got an unexpected keyword argument. Is it the other way around? Binom expect func none args 0 items max count 1000 tolerance calculate expected value with respect to the distribution for discrete distribution by numerical summation callable optional. The default is the identity mapping function k. Okay, so I guess float optional. Do we put them in nope. A parameter of the distribution. Yeah, I think this is the one. N and P. No. I don't think we should add these. There you go. That is it. Okay. So that is how we use the expect method directly. So you have to pass N and P. Next, yeah, that's the expectation. Now we'll just look at variance. So nothing much to discuss variance here. We already saw variance previously. The definition is the same. It's just in binomial. The formula changes slightly. So the definition is obviously it's the distance between or it's the difference between your center, which in this case for variance it will be mean, difference between an observation and the mean value, or you can say the distance between the an observation and the mean. And the higher the value of the variance, the more the data point is deviating from the typical value, which is the mean in this case, which means there are this can mean many things, but what this means is something's wrong with the data, what variance tells you. It might be because of something like maybe there is a bias, because if the variance is small, like within maybe 1 or 2 standard deviations, you can say that's because of chance. It's like, suppose you flip the coin 5,000 times, the probability of heads is theoretically 0.5, right? But which means 50% of the time. But in reality, you will not always see 5,000 times exactly. You won't see heads 5,000 times. If you flip the coin 10,000 times, you will not see exactly 5,000 times. You might see 5,100 or maybe 5,050 or something like that times you might see the heads, and the rest of the times you might see tails. So that extra could be pure chance, right? That could be like there are many other factors affecting it, so it could just be pure chance as long as your coin is almost fair. Like, you cannot have perfectly fair any time, but almost, if it's a fair coin, you will see somewhere around 50% values. But if it is greater than 50%, like maybe like 4 standard deviations away from the mean, then it's not by chance. Then either your coin is biased or something's happening there. So that's where that's how variance is used to find these anomalies. In this case, the variance formula is just slightly different. The formula is n times p times 1 minus p. That's your sigma square. That's the variance formula. We'll see how this comes and stuff, but for now just remember that. I think that's sufficient for this one. Now conditions of a binomial experiment. This one, let me just peek at the data directly. So these are the conditions. So there are three conditions. One is the experiment must consist of a fixed number of trials. We obviously have fixed trials in the previous example, right? 4 trials. So 4 draws of the balls. And with only 2 possible outcomes, we did have 2 possible outcomes. One is red and one is not red, which is blue. So success is when we get all 4 of them reds, and failure is when we don't get all 4 reds. So only 2 outcomes there as well. So we saw fixed n is equal to 4, and we cannot increase or decrease it in between, which we didn't. We defined success of the event as drawing red balls, which is 3 out of 5. Then the second property or the condition is individual trials are identical and independent. So what does that mean? So the probability should not change, and it didn't change, and it is independent because we had replacement, right? So each trial was independent. Right, so the probability values might change. In this example, trials of drawing balls were identical and independent as we were replacing the balls after each draw. Yeah, so hence it contained exactly same number of balls of each color. And the third is the random variable denotes the number of successes in n trials. So these are the 3 conditions for binomial distribution. Now we'll look at the Bernoulli distribution. Bernoulli is pretty straightforward, and So Bernoulli is just a special condition of binomial distribution where number of trials is equal to just 1. In binomial distribution is series of Bernoulli trials. That is all binomial distribution is. So Bernoulli distribution n becomes 1. So that's the primarily that's the definition of Bernoulli distribution. And if we can plot it, we'll see how the Bernoulli distribution looks like. We'll just hard code the values. So say x is we'll take 0, 1. It's nothing but success or failure. And y is our probabilities. We'll say the probability of reds is 3 out of let's take blues 2 out of 5, and the probability of red is 3 out of 5. We'll just plot it in a bar plot, SNS dot bar plot. So x is x and y is y. So this is the basic this is the Bernoulli distribution. I don't know what else to say here. I don't think there is much to speak about this. So I hope the x part was clear. Now x is 0 and 1 because you only have, again, the outcomes for binomial and Bernoulli are the same. It's either success or failure. You can either win or lose. There's no other option. So which is why you have 0 and 1. But for Bernoulli, since Bernoulli is nothing but series of binomial trials, so you can have something like in the first trial, say I got blue, blue, blue and red, right? Or rather blue, blue, blue and blue. I have 0 success here. So in the next trial I have blue, blue, blue and red. I have 1 success. I have blue, blue, red, red. I have 2 successes. I have blue, red, red and red. I have 3. And I have red, red, red and red. I have 4. So my um, uh, my x will be in binomial case, it will be 0, 1, 2, 3, 4, and obviously the PMFs will follow. So that is yeah, I guess that is it. If I missed anything, I will probably cover it in the next class anyway, the upcoming classes. But that's all there is to uh, distributions. Not distributions. I should say binomial and Bernoulli distribution. And essentially, we just saw the first two distributions. Yeah, I hope that was clear, and I will see you in the next video.